Since before recorded history, people have been looking at the night sky, wondering what makes those points of light move just the way that they do. Well, there are many points up there which move in a very predictable pattern. They're called the stars. But there are others, called the planets, which move in a seemingly erratic pattern. They wander around between the stars. A search for a mathematical model of how the planets move and where to find them on any given day of the year is one of the great stories in the history of science. It takes us from circles to ellipses to a fundamental force that acts on all matter, all the way up to our ability to fly rockets to other planets and other solar systems. The story is that of gravitation. But it begins in an effort to understand why the planets moved in the way that they do. And the first one to give a good quantitative model was Johannes Kepler. Kepler had access to a large database of observations made very accurately by Tycho Brahe. And he discovered that the observations of angles and times did not match with the models of the solar system at the current time that were based off of circles. So Kepler analyzed the data and found that to fit it accurately, he needed to invent 3 laws of planetary motion that were different from circular motion. The first one states that the actual shape of a planetary orbit is a geometrical shape called an ellipse. So planets travel in elliptical orbits with the sun at one focus. So we need to say a little bit about what an ellipse is and what's a focus to understand Kepler's first law. Essentially, an ellipse is a type of oval, an asymmetric circle, but with special properties. The focus is a point that's off-center from the middle of the ellipse. I've marked it with the dot here. And for the purposes of orbits, we'll describe an ellipse by several variables. The overall width of the ellipse is called 2a, and a is called the semi-major axis. The major axis would be all the way across, and so a is semi-major, or half of that. Vertically, we call the height 2b, and b is called the semi-minor axis. A circle would just have its a and its b value both equal to its radius. Another important property value for the ellipse, if we put the focus at the origin, we'll notice that the ellipse is not symmetric. There's a point here which is the closest to the origin. This is called the periapsis. And we'll label the distance from the focus to the point of periapsis as r sub p. On the other side is a point which is the maximum distance from the focus. And this is called apoapsis. And we'll label that distance as RA. So from this we can see that RA plus RP equals 2A, the semi-major axis. There's one other variable that we'll use for the geometry of the ellipse. And this is the distance along the vertical axis from the focus to the point where the ellipse crosses the vertical axis. The symbol for this is P, and it is called the Lattice Rectum, or Latin for the right length, right? Perpendicular to the major axis is a right angle. The formula for the distance from the origin at a given angle in the ellipse is the lattice rectum P divided by the quantity 1 plus the cosine of the angle multiplied by a quantity called the eccentricity. The eccentricity determines whether the ellipse is circular or whether it's very elongated. A circle would have an eccentricity of 0, making the radius constant. Most planetary orbits have a very low eccentricity value, very close to 0. They're almost circular. And that's why it took quite a long time. You had to have good enough data before you could determine that they were actually elliptical and measure their eccentricity different from 0. The quantities that I've defined up here are not all independent. If we look at the formula for the radius distance at a given angle, we can see that since periapsis occurs at an angle of 0, the distance of periapsis is equal to p over 1 plus epsilon, because the cosine evaluates to 1. The distance of apoapsis is p over 1 minus epsilon, because the cosine of the angle evaluates to minus 1. We can put these two together with the formula relating the distances to the semi-major axis to get A equals P over 1 minus epsilon squared. And by some more involved geometry, one can find out that the semi-minor axis B will be equal to P over the square root of 1 minus epsilon squared. So we could describe an ellipse in terms of A and B, its two axes, or we could describe it in terms of its distance of periapsis and distance of apoapsis, or we could describe it in terms of its lattice rectum and an eccentricity. So these are the ways, each way requires two variables to describe the ellipse. Now the planets go around on this trajectory. They follow the edge of the ellipse, while the sun sits at one of the foci. So that is the first law. The second law of Kepler has to do with how quickly the planets move when they're at different parts of their orbit. We'll write it out first. It says the line joining the planet and sun sweeps out equal areas in equal times. So what does this have to do with the speed of the motion around the ellipse? Well, if we consider some interval of time, say between this point on the motion and this point, during some time interval, delta t, the position of the planet would advance from this location, we'll call 1, to this location, we'll call 2. The line from the planet to the sun sweeps out an area which I shaded in there. We'll call it A12. If we take a look at the planet on some other portion of its orbit, say between locations 3 and 4, in the same time interval, the distance to the sun would be much longer. And so the area would be long and skinny rather than short and wide. Kepler's law says that these two areas are always equal, since we used equal times. Since a area is basically related to the product of its length and its width, if the planet is farther away from the sun, then it doesn't need to cover as much distance in that time interval to make the same area. So qualitatively, Kepler's second law says that planets travel slower when they're farther away from the sun. In fact, we can derive a mathematical relationship here if we take a look at the velocity vector at each location. Let's look at location 2 and location 3. At location 2, the velocity vector is tangent to the ellipse. But it is not necessarily perpendicular to the radius vector. This is even more clear at location 3. Here the velocity vector and the radius vector are clearly not perpendicular. So we can think of the velocity vector as having one portion which is purely tangential motion, and one portion which is its radial component of the motion. Essentially, we find the components of the velocity vector at a specific position in space. Returning to Kepler's second law, then, the area of one of these triangles is going to be approximately treating this like a triangle. So we have 1/2 the base, which could be the radius, at position 1, times the height of the triangle, which is going to be approximately equal to the tangential component of that velocity. Now, I've drawn these time intervals as quite large and have a very exaggerated, large pie-shaped wedge here. But this approximation becomes even more accurate if you get to skinnier and skinnier triangles or shorter time intervals. Here we would have R1 here, and then V theta 1 times delta t on the opposite leg. If we consider arbitrarily short time intervals, we can think of this area as a function of time and take its derivative. And we will then get 1/2 r times this tangential component of the velocity. So Kepler's law states that this quantity is constant, and since it's constant, the factor of 1/2 isn't really important. It just makes the constant different. And so we can mathematically interpret Kepler's law as a statement that says the instantaneous radius value of the planet multiplied by its tangential component of velocity is equal to a constant. This is particularly useful when we apply it to the positions of periapsis and apoapsis, because at those points, by definition, the velocity is purely tangential. Therefore, we can have, from Kepler's second law, a special version that can relate the velocity of the object at periapsis to the velocity of the object at apoapsis, and the shape of the ellipse with its two radius values. Kepler's final law, the third law, was discovered a few years later. Here, instead of looking at a single planet, Kepler looked at the data for all of the planets combined and found that as a planet moves farther away from the sun, its overall time to go around one orbit is also longer. The pattern can be summarized by saying that the period of a planet's orbit is proportional to its semi-major axis to the 3/2 power. Now this is a bit interesting. There aren't many laws of physics that involve a power of 3/2, but we will see how this naturally comes about later in the context of gravitation. So as a planet, well, the planets don't change their orbital radius, right? They have a certain value and it stays constant. But if you look at planets which are farther away, they will orbit slower. They will take longer to go around, but not in direct proportion, in proportion to the average radius to the 3/2 power. So they go even slower than they would if they were just proportionally farther away. Now, Kepler's 3 laws allow one to accurately predict where each planet will be on a given day at a given time over a long number of years. However, they leave a bit to be desired. They don't really explain why the planets move that way. They just explain how it works. The next great advance would come from one of our favorite characters, Isaac Newton. And while we tend to think of Newton as a superhero, almost inventing everything once, all on his own, it turns out that in Newton's day, most of the things that he wrote about acceleration and velocity were actually, for the most part, understood by other scientists in the same area. The reason that Newton really became famous is he took the time to write the books, and he solved the problem of how gravitation works. Newton's law of universal gravitation proposes that between every pair of objects in the entire universe, independent of what they are or what they're made of, there exists a force of attraction. Newton called this force the force of gravity, or weight. A statement of Newton's law of universal gravitation goes like this: there exists an attractive force between all objects in the universe proportional to the product of their masses and the inverse square of the distance between their centers. This means that for any pair of objects, there's a force vector. The force is parallel to the displacement between the objects in terms of direction. But the force has a magnitude that is equal to some constant times the first mass times the second mass divided by the distance between them squared. The reason we know there's a constant here is because the law only says that the force is proportional to this product of masses and inverse square of the distance. This constant was not actually invented by Newton. He used totally different unit systems and a lot of geometry stuff. But nowadays we call this the universal gravitation constant. But I'm not going to give you its value just yet because it's an interesting story how we ever figured out this value in the first place. But let's just take this proposed law at first and answer some common objections that we might come up with. First one, if we're proposing a force of attraction between everything, why don't we observe this force on a daily basis? I don't feel pulled to large trucks. I don't notice marbles on my desk roll towards each other. Why can't we tell this force is there? The answer to that is that this force is very small for everyday objects. The constant g must be very small in normal everyday units. We can only hope to observe a force if the two masses were extremely large, such as the masses held in planets. However, it is possible if we can measure force in a very sensitive way that we can detect this force. And that is actually going to be something we discuss in a bit. Second question is, okay, so let's answer that first question. Why don't we observe this force for normal objects? Question mark? Well, for normal objects, m is small. So f is small. Too small to be observed. It would be outweighed by a gust of wind. Second question. We've actually been dealing with gravity for quite a long time, but we always are careful to say that it's near the surface of the Earth. And we use a formula, F equals mg. How can this formula for force be consistent with the formula we've been using all along, F equals mg? Do we have to totally change our way of doing things, or is one of them wrong? In fact, they are completely consistent with each other as long as we understand that our motions, when we use F equals mg, don't stray too far away from the surface of the Earth. The radius of the Earth has been known since ancient times. You can determine it just by looking at shadows at different times of day. It is about 6.35 million meters. And for most of our lives, our distance from the center of the Earth is very close to this value. Even if we change our height by several kilometers, it only affects our radius to the center of the Earth by less than 1%. So therefore, if we are close to the surface of the Earth, our value to use for r in Newton's law of universal gravitation is essentially equal to the radius of the Earth itself. Therefore, our force would be predicted to be equal to g times the mass of the Earth, since that's one of the objects, our mass, or the mass of the moving object, since that's the other object, and divided by the radius of the Earth squared. Of course, this must end up being equal to mg if it's to be consistent, and therefore we can tell from this that since the value of g is known, 9.81, the radius of the Earth is known, we can determine the product of Newton's universal gravitational constant and the mass of the Earth by solving. It turns out that this value is equal to 3.963 times 10 to the 14th meters cubed per second squared. This is an important value for orbits around the Earth, and it is called the standard gravitational parameter. However, this value does not allow us to discern the exact value of g or the value of the mass of the Earth, but only their product. Let's now move on to ask a second question relating to the law of universal gravitation. I guess a third question is, how does this law actually give us orbits? Why did Newton think that this was a good law to propose? Trying to explain orbits doesn't maybe seem like you would talk about universal forces between everything. Well, let's think about what an orbit involves. It involves a very large object and a very small object. The very small object moves in a trajectory around the large object. And for now, to keep the math simple, let's just investigate if this works for a circular orbit. Surely it has to work for a circular orbit to be good for any other kind of orbit. So what's going on here? We know that an object moving in a circular trajectory undergoes an acceleration. Otherwise, it would move in a straight line. Therefore, it must be under the influence of a net force. This net force we've worked with before. It's equal to the mass times the velocity squared over the radius of the circle. It's called the centripetal net force. But Newton's proposal says that this centripetal force actually arises because of an attraction between the two masses due to universal gravitation. The force having magnitude gmm over r squared. Well, if we go to solve this for the speed of the orbit, we can do so quite easily. We'll just divide both sides by m and multiply both sides by one factor of r and then take the square root. We find that the speed of an object in an orbit under the force of gravity would be equal to the square root of gm over r. But is that any good? How could we test this? Well, one way to test it is to look at some known orbits and to take a measurable quantity, their period, and compare it to our prediction. How do we get the period of an orbit? Well, it's moving in a circle at constant speed, so we just need to take the total distance it travels, which is the circumference, divided by the speed of motion. Since we have a formula for speed in terms of the radius of the orbit, we can plug that in, and we get that the period of the orbit is equal to 2 pi times the radius to the 3/2 power divided by the square root of gm. The 3/2 power comes from the r in the circumference multiplied by the square root of r in the velocity. And we have a wonderful discovery here. We've now used Newton's law to predict that the period of orbit is proportional to its radius to the 3/2 power. That was Kepler's third law. So Newton's law seems to have a power of predicting Kepler's laws with just one concept, a universal force of attraction. Let's test this formula further, though. A great object to test this on is the moon. We all know a bit about the moon, and we can measure some of the properties of the moon with ease. Remember that for an orbiting object around the Earth, the quantity gm was equal to 3.963 times 10 to the 14th meters cubed per second squared. The radius of the Earth-Moon orbit, or the distance between the moon and the Earth, is actually not a constant, because the moon's eccentricity is not 0. But a good average value to use is 3.85 times 10 to the 8th meters, 385 million meters. If we take these two values and plug them into our prediction formula for the period of the moon's orbit, we get a time of 2.384 times 10 to the 6th seconds. Now that value might not seem so familiar to us because it's in seconds, but if we divide this by 3,600 and then divide it by 24 to convert it into days, the period is 27.6 days. That's 1 month. That's the period of the moon's orbit, predicted entirely by the law of gravitation, the distance to the moon, and from the gravitational parameter, which we got by knowing the radius of the Earth and the acceleration of gravity on the surface of the Earth. So this is great evidence that Newton's law of universal gravitation is correct for predicting the orbits of smaller objects around large central bodies. Let's do a fun example that we'll need for a value later on. It says, based on the orbit of the Earth, calculate the value of the gravitational parameter, gm, of the Sun. Well, our formula from Kepler's third law, solved by Newton, would tell us that 4 pi squared times the radius cubed over the period is equal to, over the period squared, is equal to this gravitational parameter for the Sun. We have to plug in the radius of the Earth-Sun orbit and the period of the Earth's orbit. We know both of these from astronomical observations. The radius of the Earth-Sun orbit is 1.496 times 10 to the 10th meters. That gets cubed. And the period of the Earth is 1 year. But to make the units work out, we'll need to express it in terms of seconds. That's 3.154 times 10 to the 7th seconds. And that gets squared in the denominator. So putting these numbers together, we get a gravitational parameter for the Sun of 1.33 times 10 to the 17th meters cubed per second squared. And that value is now a property of the Sun. It's related to its mass and a global universal constant. So it could be used to predict the periods and radii of all other sorts of planets, asteroids, anything that orbits the Sun. Now let's move on to this question of, is there a way to find out the value of the universal gravitational constant explicitly? And the answer is yes, but we have to do a very sensitive experiment. This experiment was first done by the English scientist Henry Cavendish in the year 1797. It's a famous experiment in physics called the Cavendish Experiment. What Cavendish did was acquire a large amount of lead and smelt it into a spherical shape. He had one lead sphere which had a mass of 158 kilograms and a second lead sphere of a mass of 0.73 kilograms. The reason to use lead is because it's very dense, and so you can make a very heavy object without having it be too large. Cavendish used a sphere of radius 0.3 meters for the large and 0.051 meters for the small. The distance between the surfaces of the spheres was 0.23 meters. This means that the distance between the centers of the spheres was 0.4055 meters. In this case, Cavendish was able to measure a force of attraction between these spheres, a very small force, and he was very careful to get this measurement. The force was measured at 4.73 times 10 to the minus 8th newtons. Now we have a situation where, if we compare it to the law of universal gravitation, we've measured the masses, we've measured the distance between them, and we've measured the force. So this can be used to calculate explicitly the value for g. We could have always done this, but relying on the Earth to be one of the objects means that we couldn't really measure its mass by any normal method. Cavendish was able to measure the mass of these spheres by normal methods, on scales and so forth, and get an independent value for them in kilograms. So doing this experiment allowed him to calculate the value of g, and it was 6.743 times 10 to the minus 11th Newton meter squared per kilogram squared. And this value has the same, this constant has the same value for anywhere in the universe where it is applied. It is a universal constant of nature. Or, alternatively, a constant that arose because of our human choice of unit systems. Now, a scientific report on the value of the universal gravitation constant wouldn't have gotten much attention in the press. So Cavendish sold his work by calling it weighing the Earth. And we'll do this as an example. If we know the value of the gravitational constant now, we can find out the value for the mass of the Earth. We just take the standard gravitational parameter for the Earth and divide it by Newton's gravitational constant. The result is a large amount of kilograms, 5.87 times 10 to the 24th. It's such a large number, it kind of defies our normal interpretations of mass. This isn't a million or even a billion kilograms. It's 10 to the 24th. How can we interpret that? Well, one way to do it is to look at the density of the Earth. Density, remember, is mass over volume. And since the Earth is approximately a sphere, we can use its radius to get its volume. Mass on the top, and the formula for the volume of a sphere on the bottom, 4/3 pi r cubed. This calculation yields a value of 5,464 kilograms per cubic meter. And this is a very interesting result. What substances we have on the surface of the Earth that we can easily measure the density of? Well, we have water, which is about 1,000 kilograms per meter cubed. So the Earth is denser than water. We have air, which is about 1.2 kilograms per meter cubed. So the Earth is not made up of much air. There are a large number of different types of minerals, rocks, but they all have densities that are in the range of about 1,500 to 3,000 kilograms per meter cubed. So the Earth is yet heavier than it would be if it was made purely of rocks. The densest objects that we have in everyday experience are metals. And metals have densities between 8,000 and 12,000 kilograms per meter cubed. So the Earth is less dense than a pure chunk of metal. It appears that the Earth is somewhere between partially composed of metal and partially composed of rock. In fact, Cavendish's experiments was very important in the early studies of geology to try to find out what the Earth was actually made of by knowing its density. And the same technique is still used today on other planets, asteroids, moons, and so forth to get a guess at what they might contain. One final topic that I want to address is Newton's law and its relationship to Kepler's laws. We already saw that using the equation of uniform circular motion, Newton's law could be used to prove Kepler's third law, at least for a circular orbit. The other one that we can prove easy is Kepler's second law. Remember that Kepler's second law stated that this derivative dA dt, 1/2 r times v theta, was a constant. We could also write this as r times v theta is a constant for a particular planet or orbiting object. Let's try to approach this same idea with Newton's second law and Newton's law of gravitation. In fact, for this proof, it won't even matter how large the force of gravity is between the objects. It will only matter that the force of gravitation is parallel to the displacement vector between the objects. The displacement vector points from one object to the other, and the force also points from one object to the other, so they're parallel. So that means that when we go to calculate a torque, that might be caused by the gravitational force, we get identically zero, because two vectors that are parallel or anti-parallel plugged into the cross product give us an angle of 0 or 180 degrees, which always results in 0. So the gravitational force of attraction produces no torque on the orbiting object. It cannot change its angular momentum. Since L is changed by torque, if torque is 0, then L is constant. And an orbiting body that's small essentially behaves as a point particle, and the angular momentum would then be given by its moment of inertia, mr squared, times its angular velocity, omega. One final transformation here is to take one of the powers of r and multiply it by omega, since r times omega gives us the tangential component of velocity. We see that Kepler's second law is actually synonymous with conservation of angular momentum. The constant that things are equal to in Kepler's second law is actually equal to 1/2 the angular momentum of the particle divided by its mass.